Remember to ask your questions throughout the presentation in the Q&A box. Make sure you click on the arrow to submit.
For 125 years, the Penn State College of Engineering has been a leader in education, research, innovation, and inspiring change around the world.
Since our earliest days in the late 1800s, our buildings have changed, our demographics have changed, our funding has changed, and our research has changed. The passion of our people has not changed. It is the energy of our students, our faculty, and our staff that get poured into the forward momentum of education and research, seeking to impact the world and advance human society. It is the passion that pushes us to do more and to be better. We are the Penn State College of Engineering, and we are just getting started.
Good morning, Simio. We are Justin Rist and Rob Newton from the Penn State Department of Industrial and Manufacturing Engineering. And Simio made the egregious error of inviting us to introduce the student competition from this past spring. Very quickly, we will introduce the problem the students were given, followed by the winning team introduction and project videos submitted by the two stunning gentlemen you see on the screen right now. We will then happily answer any questions you may have after the videos. Ideally, these questions would be focused on the competition submission, but Justin is likely open to sharing his techniques on the perfect cup of espresso as well. Over to Justin.
So what was the problem? The Simio Shelving Shop, beyond being very difficult to say 3 times fast, had low order fill rates as a result of raw material stockouts. It was hypothesized that the issues resulted from the company's static buffer inventory policy. Management tasked us personally to test this hypothesis and evaluate a new inventory policy using demand-driven materials requirement planning. We were provided 3 months of production data from the factory with which we built models in Simio for both the current and proposed inventory policies. The inspired recommendations we produced saved the factory millions easily. In hindsight, with Simio's newly configured shelving boom, we should have negotiated stock options as compensation for our hard work. But the satisfaction of knowing we helped a company that does not actually exist is reward in itself. Let's play our team intro video first, and then afterwards we will show you the answers we came up with.
Hi Simio, I'm Rob.
And I'm Justin.
And we're here to build some shelves.
Rob, we're not cutting wood. We're using this.
All right, let me see it. All right. I don't know how many shelves we'll be able to make out of this thing, but we'll give it a go.
Rob, no!
I told you this would come in handy.
Hi, I'm Rob Newton.
And I'm Justin Rist,
We're graduate students at Penn State University.
in the Department of Industrial and Manufacturing Engineering.
Hi, I'm Rob Newton. Justin, over here.
Sorry, my glasses are fogged up again.
No.
Hey, I'm Justin Rist.
Hi, I'm Rob Newton. Dang it. And Dr. Song said if we did this, we wouldn't have to do any more homework.
Hello and welcome. This is our submission to the May 2021 Simio Student Competition. Today we will be quickly discussing our analysis of the given data for the problem, the model we built, its verification, validation, and results, an evaluation of potential new suppliers for oak planks, and finishing with our recommendations for the factory. Diving right in, we were provided processing times for each station in the factory, as well as supplier quality and lead times. Regarding supplier lead times, we found a nearly discrete uniform distribution for each supplier, which did simplify our inventory resupply model. Through matching the first 4 moments and use of quantile-quantile charts, We found the triangular distribution matched well for each workstation on the factory floor. An example of this analysis is included on the slide for the drilling station in the shelf assembly cell. It should be mentioned we did not observe large differences between like stations within a cell, nor did we find the type of wood affected processing time. But we did observe the type of shelf, specifically the dimensions, 2x2, 2x3, 2x4, did affect the processing times. One interesting case we found when fitting our distributions was the bimodal nature of the cutting station in the shelf assembly cell. The use of scrap wood, only available for 2x2 shelves, was a significant factor in the processing time at that station, with the use of scrap wood reducing cutting time by approximately 20%. To implement this unique case, we added Boolean values to the equations governing the station, as you can see in the example formula breakdown on this slide.
Now I will give a tour of our modeled shelving factory. First, orders are received daily to the sales department, and release timing is facilitated with a work schedule. Add-on processes are triggered upon order release, sending subassembly request entities to each area of the plant. Each request entity is assigned a state variable according to the entity's shelving type to facilitate proper processing times at each station. Let's take a closer look at the shelf assembly area. Shelf entities flow through each workstation server. Raw materials, tracked using state statistics, are decremented upon subassembly processing. If a process is starved of raw goods, the process server will fail and production will cease until the inventory is replenished. After processing, add-on processes facilitate raw good requests if inventory store is below the reorder point and no order has already been placed for that raw material. Server entities in the raw material order area and work schedules facilitate raw good lead times and arrivals. When the raw good entity arrives to the plant, it goes to the inspection server. Inspection processing time and order quantity reduction due to quality issues are controlled with add-on processes. After inspection, the associated state statistic is incremented and the associated workstation can resume production. All cells within the plant work in a similar manner to meet the daily order demand. Below the production floor, key performance indicators are displayed along with buffer costs and quantities information to validate correct operation of the plant. Now we want to highlight a few unique aspects of our Simio model, starting with our process for managing inventory buffers. The example on the slide is the back panel attached station in the final assembly cell. Processing a shelf at this station requires a final assembly, a back panel subassembly, and wood screws. The station is modeled as a combiner object. The final assembly and back panel are represented by entities. The combiner allows entities to enter the processing area only if the shelf type of both subassemblies match. Upon processing, the model decrements the wood screw buffer using an add-on process, shown on the slide. If it is not depleted, the process decrements the inventory buffer, then checks if the buffer has dipped below the reorder point. If it has dipped below, a refill order is sent to the appropriate server. If the buffer is depleted, the combiner fails and processing is suspended until the buffer is replenished. In preparation for the challenge problem, we created a new model with the added property which supplier. This property is a Boolean value that simulated multiple suppliers within the same model. Changing the value in experimentation allowed the evaluation of different suppliers with direct comparison of simulation results in the same experiment. Here are the two representative charts tracking inventories for both the current state and DDMRP configurations. The current state shows the static reorder point and max inventory levels. The DDMRP chart shows the dynamic red, yellow, and green zones for inventory management. In both cases, when the inventory level dips below the reorder point or red zone respectively, an order is made to the corresponding server, validating that the model is placing the order at the proper time. Per the given data, orders are placed at 5 p.m. on the day they dip below the respective threshold, coordinated by a Simio work schedule. Upon arrival to the plant, materials are moved to the inspection station and inventory levels are incremented to include the materials received. Simulating the model's baseline configuration revealed that the factory was unable to meet customer demand with its current inventory policy. This policy led to a fill rate that was essentially zero in steady state, riddled with stockouts, and with throughput and production times unable to satisfy the customer demand. To further validate the model and set a benchmark for optimal performance, the baseline was resimulated with raw material lead times set to zero. After eliminating these lead times, the factory was, in fact, able to meet demand, suggesting the need for an improved inventory policy.
To use the DDMRP inventory model, we had to set 2 factors for each material, 14 in total. With such a large set of possible configurations, it was not possible to test each configuration manually. Instead, we took advantage of the OptQuest add-in to generate reasonable sets of parameter configurations, prioritizing fill rate in our objective function, but also accounting for inventory costs. We then evaluated these scenarios using the Kim and Nelson ranking and selection procedure also built into Simio. We first eliminated any scenario from OptQuest that exceeded $50,000 in average inventory costs or did not meet a fill rate threshold of 65%. This left us with 8 scenarios to evaluate using Kim and Nelson, which allowed us to identify the best possible configuration. As shown in the box plots here, none of the 8 scenarios had a significant difference in fill rate. One scenario, however, did stand apart as the best in terms of inventory costs. For the challenge question, we needed to generate new parameters for the DDMRP inventory policy for the potential suppliers of oak planks. This was done in a similar manner using OptQuest to generate reasonable configurations. Using the Watson Lumber Company marginally increased fill rate. Unfortunately, this supplier increased inventory costs significantly. As a result, we found the marginal gains in fill rate with the supplier did not justify the significant cost increases. Whereas using Pacific Timber did reduce inventory costs, this was an artifact of constant stockout seen using the supplier that led to significantly reduced throughput and increased production time. We did not recommend either of these potential suppliers. Which brings us to our recommendations. We found the DDMRP system improved the fill rate, throughput, and production time. Inventory prices did increase, but the trade-off with these other metrics and the reduction in stockouts should justify the new system. As a result, we recommend the DDMRP system with the parameters we provide in our included report. Additionally, we recommend renewing their current contract with Hayes Lumber for oak planks, based on our discussion from the previous slide. One quick postscript. In our simulation, we found using the DDMRP system in our recommended configuration brings the factory to near optimal performance. The utilization of the cutting station in the shelf assembly cell in this configuration becomes the bottleneck. Further improvement is possible in the factory, but this bottleneck needs to be addressed to realize it. For example, adding a second cutting station in the shelf assembly cell. This concludes our presentation. Thanks very much for your time and consideration on this project.
Well, thank you so much, Rob and Justin, for a great presentation. If you don't mind, we have some great questions from the audience. The first question was, what motivated you to join the Simio student competition outside of you obviously not having to do homework?
Can I go first on this one, Justin?
Sure. Yeah, I was gonna suggest that anyway.
So Justin and I were both taking a discrete event simulation class together, and he used that as the in for the homework to incentivize me. But effectively, this was all Justin's idea, and we had a lot of fun doing it. But I definitely want to hear how Justin feels about this, because the reason that I got motivated to join was because Justin essentially told me it was the right thing to do.
Yeah. So for me, I was I'm in my second year at Penn State, but before being at Penn State, I was an undergrad student at Auburn University, and there was a professor there, Dr. Jeff Smith, that taught me Simio. And as part of his class, his discrete event simulations class in undergrad, we had to enter this competition. And entering it then with very limited knowledge of Simio, like I was just learning it, I was able to get an honorable mention. And so I knew that if I had very limited knowledge then to enter the competition, and I did okay in it, I would have a better shot this time to enter and maybe get better results. And so I saw it kind of as a challenge, and Rob was willing to be roped into it. And with us working together, it turned out into a really good project.
Would you say that your 2020 submission was missing an it factor, Justin? That you needed one last piece to really take it all the way across the line?
Nothing comes to mind really when you mention that. I think it just, getting better over time.
It's funny. So at the competition, a two-part question. What were key learnings you experienced from the competition? And are there any, quote, lessons learned from the competition that you will bring with you to future projects?
Yeah, I can answer this one first, and I'll let Rob add his thoughts. So the biggest thing that I learned when building this model for the competition, the problem statement essentially gave us things that we were allowed to change within the factory production floor to improve this inventory policy. And the things that we couldn't change were the production times and the actual workstations. The only layout things we could change within the factory floor were we could consolidate where the material stores were. So in many cases, there was a certain material that was used to create the shelves that was stored in two different spots within the factory that were replenished completely independently of each other. So we were allowed to combine those with the trade-off of having more travel time between the stations and things like that. Initially, we thought the obvious path there was to just consolidate inventory stores as much as possible to make the buffers bigger to lower the variability. So we did that, and we found out that because the different cells of the factory had different throughputs, essentially the higher throughput cells would hog all the material and lead to a ton of WIP that backed up at the end of the cell that was waiting on the separate assemblies to be added to it so that we could produce the final shelf. And so it really threw the whole factory out of balance, which is not something that I expected at all, and really goes to show the value of simulation and modeling these problems, because a lot of times the obvious change that appears like it makes sense on paper is not really what would be a good change, and simulation can help you find that problem before you actually implement it and throw a factory, for example, into chaos. And really that goes well into the lessons that I learned. I think it shows the power of discrete event simulation and Simio to really find these problems and find the right solutions before committing to implementation of these solutions in a real world environment.
The only thing I would add is the interface and the way that you were able to capture the metrics that were of interest. Very intuitive, and as we showed a couple times in our presentation, if you only looked at average inventory cost, if you only looked at fill rate, you would not necessarily get the answer that you needed with having the full picture. And just being able to produce all those results and look at multiple criteria in a bunch of different scenarios was hugely useful and beneficial for our analysis.
For this problem, which element of the problem did you find most challenging to solve?
I mean, challenging is an interesting adjective, just because there was. So I think I know what Justin's answer is, and I don't want to steal his thunder. I will say, though, that when we were given the data for 3 months, we weren't quite sure how best to approach it. Did we need to go and use random generation to create a full year's worth? Were we going to have enough to use to generate adequate distributions just with the data we were given? Ultimately, the answer to that question was yes. And as we showed with our analysis of the moments, we were able to come up with solid distributions that were able to model the factory pretty well. But Justin, some of the hangups and choke points that you found that you were able to come up with some pretty creative answers for. I really think that's probably what needs to be discussed more. Yeah.
Yeah. So I can take it from there. So probably the most challenging thing we ran into when modeling it is once we had this model working well and we had all the information validated to make sure the model was working right with this new inventory model. This DDMRP inventory model that was recommended in the case has two user like parameters that can be changed on a scale of like 0 to 10 for each material buffer. And there was, I believe, 8 material buffers in this problem. So that leads to just a huge amount of combinations of these inputs that could be tested, which even in a pretty simple model like this that we were able to run on our laptops, it became just computationally unpractical to test all of these combinations. And so before this project, I didn't know about some of the plugin tools that we mentioned in our presentation and about how they can be used to essentially solve this problem in a computationally efficient way and find maybe near optimal values for this many parameters. So we used, I believe it's called OptiQuest as in the project, and it helped us to relatively quickly find a lot of these user inputted parameters. And then it allowed us to compare the alternatives and test and show which one was actually best. And it ran all within a couple of hours, which compared to what we were expecting was not too bad at all.
Did you find while doing the student competition there was any problems with social distancing and what happened with COVID? Because we were still in those times.
We poked fun at that a little bit in our intro, didn't we?
Yeah.
I mean, it's. I have all the respect in the world for the teams that did this a year ago, where they just were not allowed to see each other. Justin and I are both grad students, and we work closely enough with each other that we went ahead and assumed some of that risk. And when you're talking about, some of the late nights that come with putting together a final product that we would be comfortable submitting to Simio for international competition, doing all of that socially distanced would have been much more challenging. However, I mean, it's software, and there were plenty of other options in what we were able to go back and forth with. But the challenge does need to be honored, that it would have been much more difficult without our opportunities to just spend some time with each other.
Now, I would not be a marketing person if I didn't make a plug that our current student competition is open. We have our December 2021 competition. And the final question for you is, what advice do you have for those currently participating or who are thinking about participating in the student competition?
Advice that I have for that. So first of all, start early. I'm not sure if that news is coming late. There's always more challenges that come up than you expect. But the other thing I would add to that is read the problem statement. Read what the hypothetical situation. Read exactly what they want out of your project and deliver that. Don't try to add anything extra or fancy are just unnecessary until you've achieved the baselines of what the customer is asking for. Because often you'll find that if you try to add extra, it'll end up just getting bogged down and you'll never be able to complete the project. And in reality, what the customer wants is exactly what they ask for, and they'll be very happy if you supply the best answer to specifically what they're asking for.
I also hope it was apparent that we were having fun with it it's not unstressful to to come up with this stuff, but I hope it was apparent that we had fun with what we did eventually put together. And I feel for the undergrads that might be doing this with some people that they don't know in their simulation class. Like Justin and I had the benefit of being friends beforehand, and it's a cool opportunity to see what other people's strengths are. And once you can hit a nice flow, and enjoy yourselves while you're working on a problem as nerdy as simulating a shelving shop, then that makes it worth it.
Yeah, I'll credit Rob with all the humor. If it were completely up to me, the presentation would probably be a little bit less entertaining than what it was.
Well, thanks again for presenting today with our 2021 first virtual Simio Sync, and congratulations on winning the May 2021 problem. I know it was a very difficult problem. And for anyone watching, you have any questions about the student competition or the academic program, feel free to email academic@simio.com. And for any commercial companies out there listening too, we are always looking for problems that you are having with your companies that we can help solve. And the Simio student competition is a great way to A, solve your problem, and also B, recruit talent. And so you can actually see what people can do within Simio with a student competition. Thanks again, Rob and Justin, for a great presentation and great question and answers. And have a great rest of your day.
Thank you so much.
Reached the end of our 3-day agenda. I hope you enjoyed this year's conference, and what you heard and experienced this week has inspired you in your digital transformation journey. Once again, on behalf of the whole Simio team, I would like to thank each of our presenters and all of you in attendance for making this an exciting and informative Simio Sync. We look forward to returning to an in-person event for Simio Sync 2022. I wish all of you good health and great success with your digital transformation journeys. With that said, I declare Simio Sync 2021 closed.